Okay, so I'm going to be solving this problem. You want to use the Fourier transforms to solve, again, this is just the standard diffusion equation. But the interesting thing here is that our initial data is going to be some of these Dirac masses. So there's kind of like a Dirac mass at every single point, at every single integer, at every single non-negative integer. That's what this is here. But again, the reason I'm doing this is because people wanted practice with Dirac masses, and here's an infinite number of Dirac masses. Okay, so again, take Fourier. The first thing is going to be to take Fourier transforms of both sides. And when we do this, so a line, I like to use a line instead of anything else, and the star just means there's not going to be a number there. Like it's not going to be an equation that has a number. Okay, so Fourier transform of the left-hand side is just going to be the t derivative of u. The Fourier transform of the right-hand side is going to be minus c squared times the Fourier transform of u. This is a ordinary differential equation in the t variable, a first-order ordinary differential equation. So the solution, I'm not even going to do much to do the solution. The solution is just going to be the Fourier transform of u is going to be equal to the Fourier transform of u evaluated when t is equal to 0 times e to the minus c squared t. And what is u of x 0? Well, I mean, what is the Fourier transform of u? It's just going to be the Fourier transform of the initial condition. But I'm gonna actually kind of think about what the Fourier transform of the initial condition could be, or we don't actually need to consider what the Fourier transform of the initial condition could be because we're going to use convolution. So again, just like for shorthand, I'm going to write this as the Fourier transform of g, which is just going to be the initial condition, times this. And I'll write this where g of x is just equal to the initial condition, u of x 0. Okay, so we know, so again, I've found the inverse Fourier transform of this one so many times. I'm not going to do it anymore. The inverse Fourier transform of this guy is 1 over the square root of 4 pi t times e to the power of minus x squared over 4t. So by the convolution theorem, okay, so why can I use the convolution theorem? Well, this is a product of two Fourier transforms, and so the inverse Fourier transform is going to be the convolution of the inverse Fourier transform of each of these pieces. So we're going to have u of xt, u of xt is equal to, okay, I'll put this stuff on the outside, times the integral from minus infinity to positive infinity, and it's going to be g of y times e to the power of minus x, x minus y, not 6, x minus y squared, 4t dy. Okay, so let me make sure I have everything compiling correctly. Okay, so what's the problem? So I see up there's a problem. I don't know where the problem is. Oh, I've got 2 C's on one of these fracts somewhere. Oh, there we go. Okay. All right, yeah, so this is what I want it to look like. And by the way, there's a reason, you know, we keep writing the same thing over and over again. There's a reason we have the fundamental solution. because it makes it easier to just write g of y, big phi of x minus y, t, dy. Okay, it's easier to write than all of this exponential stuff. Sometimes you want to see the exponential stuff. Sometimes you don't want to see it explicitly. So I'm going to write it like this, so now you can look at it both ways. Again, and the fundamental solution is just the exponent here divided by the square root of 4 pi t. Okay, so now let's actually think about the Dirac, or the initial condition. So I'm going to do this in 2 lines. And I'm not sure right now, at this point in the typing process, I'm not sure whether I want to use whether I want to use this form or this form. In other words, whether I want to have the phi symbol or actually write out what the fundamental solution is explicitly. It's just going to kind of depend on how the analysis of this part goes, the initial condition. So now we will use that u of x0 is equal to the sum of these Diracs. And I don't want to write it all out, so I'm just going to do a little copy and paste. Okay, now the good thing is, in the solution, the Diracs are only going to show up in an integral, which is good because Diracs only have definitions. Well, Diracs really only have definitions when they're involved with an integral. So now we're going to use this fact, and the above is, okay, so it's going to be u of xt is equal to the integral minus infinity to positive infinity. Okay, and we're going to look at the sum, k equals 0 to positive infinity, times the deltas, and then times the fundamental solution. But actually, I'm going to write the fundamental solution right here first. Just like this. Okay, so let me see how that looks. Okay, so what's going on with the Diracs? Well, the Dirac at each k, so I'm actually gonna take one step. I'm gonna pull the sum outside of the integral. We're gonna have something like this. Okay, and so now let me compile and we can see what we have. Okay, so let's look at this right here. So if I look at the integral, what does a Dirac do? Well, it just says that wherever, look at the variable of integration, it's y. Wherever you see a y, you're going to put a k, and that's just what this is equal to. So then this is going to be equal to the sum, k equals 0, to infinity of the fundamental solution evaluated at x minus k, comma t. Or if we want to use exactly, if you want to use what the fundamental solution is, sum k equals 0 to infinity, and we're going to have 1 over the square root of 4 pi t times e to the power of minus, and we'll have x minus k squared over 4t. Okay, and so that is the sum here. I don't know if there's a whole lot more that we can do. I do think I want to put this outside of the integral, or outside of the sum, so it'll look like that. And so the question is, does this converge? And the answer is yeah, absolutely, which is both the pun and the truth. Because what's going on here, well, we're summing a negative exponent. And so as k gets big, x minus k squared gets big, and so this is definitely summable. It's like kind of, it's even better than a geometric series. So this is definitely something that is summable. Okay, so that is the solution to this problem. That's all I got for this problem. I hope this was helpful.